Good morning, everyone. You were at the party last night. You'll be pleased to know that we've moved the dawn back to 9:30. So welcome to the dawn of a new era. I'm Phil Nash, developer advocate at JetBrains. My handle on Twitter. I'll show it again at the end, just in case you want to unfollow me at that point. If you do want to talk about any JetBrains products, C-Line, ReSharper, C++, AppCode, you can catch me afterwards. I should be here all day. But this morning we're going to be talking about error handling in C++. That's the past, present, but mostly the future, or possible futures of error handling in C++. But before we do that, we really need to look at a little bit of history. Actually, I've got a couple more seconds on this animation to go through, because this is not the first talk I've done on this subject. In fact, last year I was doing a talk at a number of conferences called Optional is Not a Failure. And this is really sort of the follow-on from that talk. I wouldn't quite say it's part two of a two-part series, but it does sort of naturally follow on. I'll get to the history of that in a moment. What we're really talking about is this proposal here, P0709. Up here it says R2, it's actually on R4 now. Most people have heard of this now. The full name is Zero Overhead Deterministic Exceptions, Throwing Values. A lot of people know it as just static exceptions, or in some cases, herb-ceptions. But what really is in it? There's actually, it's quite a long proposal, and there's a few optional parts. But there's also a number of supporting proposals. And these are all details that I alluded to at the end of my previous talk. And it's really what I want to dig into more on in this talk. But because not everyone is familiar with this proposal, I'm going to do a little bit of a summary of the high level of that at the start of this talk. But I mentioned a bit of history. I said I've been doing this talk last year, Optional is Not a Failure. So that's me at Meeting C++ last year, so almost exactly a year ago. But before this, I actually did another talk of the same name at a mobile developers conference, and this was in the context of Swift. And the reason I did this is because I felt at the time, and I still do actually, that Swift has one of, if not the best error handling strategies of any language today, which is quite a bold claim. I didn't think that the Swift community at the time, in general, fully appreciated that, so I wanted to raise awareness of it by going into what it was actually giving them and what was actually going on under the hood. And that was quite well received, I thought. But what I noticed was a lot of the same things in that background were starting to happen in C++. We're starting to go in the same sort of direction. In fact, most languages have been going in this same direction. But I thought we're quite a long way from it, still in C++. So I wanted to start to raise awareness in the C++ community of where we could be going and what we could be doing to get there. And that was why I proposed a talk with the same name. But then before I actually gave that talk for the first time at C++ Now last year, something happened. That proposal that Herb wrote, P0709, although I didn't have that paper number at the time, I became aware of it and quickly noticed that we're actually talking about almost exactly the same thing. So we're already much further along than I thought, although this is still at the proposal stage. But going a little bit further back still in history, it's not the first time I've been thinking about alternate error handling strategies in C++. Some time ago, I started playing with something called exploding return types. Who here's used exploding return types? No one? Anyone heard of exploding return types? One person, yeah. Never really caught on, but I quite liked the idea at the time. I first heard about it, I think back in 2007, talked by Andrei Alexandrescu. Choose your poison, exceptions or error codes. The idea being, not always one is the right choice over the other. Be nice to have the choice. And it really centered around this template, likely T, and had a number of different properties. In particular, what will become more important, this idea that it could hold a value of one type or the other. You have a choice in there. But for our purposes right now, is this bit. The destructor may throw if you haven't actually checked which one it is. Hence the exploding return types. So it forces you, at least at runtime, to have actually checked your return type to see whether it contained an error or not. So that was the interesting bit. And even that wasn't the first time this came up. I actually tracked it down to a post on C++ lang moderated from 2000, from Ken Hagen. He proposed this thing. Again, the important bit is the destructor freeze, if you haven't checked it. And even then, there was talk in that discussion thread about earlier work, particularly by Lisa Lippincott and James Cairns. And I like this, this comment from Lisa in the same thread. Let's not repeat the mistakes of the past. Model the copy construction and assignment on the current auto pointer, not the old broken one. Completely different time, isn't it? So that was exploding return types. So they never really caught on. And when we actually got C++11, obviously destructors no accept by default. So that really sort of put the final nail in the coffin of exploding return types, I think. So then Andre popped up a few years later, talking about a little bit of a refinement on that earlier idea. So this talk, C++ and beyond, systematic error handling in C++. He presented another type. Talk about what it's called in a moment, but it has that same property. Let's get a clear review of that slide, of holding a value of one type or another, the actual value of the type you wanted or an error type, and a way to check it. We didn't have the exploding return type this time. We realized that that was the most important part of this concept. We called this expected T. So either T or the exception preventing its creation. Instead of exceptions in there. Now expected may sound familiar. We now have a proposal for stoodExpected, which is stoodExpected, not gone in yet, still on the table for discussion, but looks like we should get that at some point. If you don't want to wait, there's boost expected, there's other third-party libraries that will give you the same functionality. Fairly straightforward, so you can have that today. But none of this is unique to C++ or new to languages in general. Here's a number of programming languages that I'm familiar with which have something similar. Most of them it's called result. In Haskell, there's a more general concept called either. But in each case, it's something which holds either a value of the type you wanted or something else, usually an error type. Interesting to note that Swift only got result as of Swift 5, which came out earlier this year. I said earlier that I thought that Swift had one of the most advanced error handling strategies of any programming language. So how come it was so far behind on this? Well, that's because this is really a stepping stone to where we actually want to be, as we'll see. And Swift sort of leapfrogged over that whole thing, went straight to the final solution, and has gone back and added this because there's still some value in having this, particularly for async programming and other cases where you need to like store the intermediate value before you process it later. That's why it's only just got it now. But it's a really important stepping stone, really important to understanding where we're actually going. So, okay, how do you use result, or in C++'s case, stoodExpected when we get it? So here's a really simple example of a function which just parses an integer out of a string. So taking a string view here, that's not that important. Here's the important lines of code. So it returns a stoodExpected of int, and in this case, I've made it stood domain error. It doesn't have to be an exception type in the case of stoodExpected, often is. And then in the case of a failure, we return this stood make unexpected, so it's a factory function, just to make overloading a bit nicer, of stood domain error. And you can construct that however you want. In the happy path case, so that's grayed out at the end, we just return the value you want. So it's actually quite simple to use. And that's stoodExpected. In use, we'd have a bit of code like this. So we'll call our function, capture the return type. We can test it as if it was a pointer or stood optional, just using the Boolean operator. And we can get the value out using the dereferencing operator, again, like stood optional, like pointers. But unlike stood optional, this is really the only difference at this point. In the case of an error, we can say .error and get the error type out. And because in this case it's an exception, we can say .what. So pretty simple, pretty straightforward. Nice and easy to understand, nice and easy to use. But here's the problem. The ratio of the happy path to the error path, even in this simple, trivial example, starting to be dominated by the error handling. Well, that was the whole problem that invented exceptions to try and solve. You know, get rid of the boilerplate around error handling, push it off to the side. We're bringing it all back again. So simple and straightforward, but a bit verbose. And that's that simple example. It gets much worse if you start to try and compose these functions together. Let's have a look at what that looks like. Let's add a couple more functions in. So I'm going to add this one, just to divide two integers and test for division by 0. So it's not an example, but just to illustrate the point. Again, returns as stood expected, and tests for that using stood make unexpected. And we'll throw one more function in that doesn't have any error handling, just takes an int, returns an int, just to see how that goes in. And what we want to do is just sequence these three things together. This is the sort of code that you might write. Call the first function, capture the result, test that, and then we pass the result on and so on. Again, when you read through it line by line, it all makes sense, it's simple, straightforward, but it's really verbose, really dominated by the error handling. Lots of heavy nesting, even in this fairly simple example. And the happy path ends up sort of in the middle there. So it's not really scalable code, I think. You can certainly do it. People have done it for years, but it's not the nicest way to do things. This is the problem with this approach. But remember that list of other languages we looked at earlier that had something similar? If everyone's sort of going this way, how are they dealing with this problem? Some of those languages are either functional languages or functional first languages. Functional languages have had approaches to this for a while. I should point out, there is one way to clean this up a little bit, of course, which is to use early returns. That does help, but it doesn't completely solve the problem. It just makes it a little bit nicer. But the real way to deal with this is to recognize that what we actually have here is a monad. So of course we're going to talk about monads. So we'll now have a little half-hour presentation on monads. No, just kidding. We don't really need to understand what monads are. What we do need to know is what the operations are that are useful. So another proposal. This is P0798. I think this actually got into 20 in Cologne. So we're actually getting this one. But this is written for stood optional. So what we're getting in 20 is for stood optional. But if you just replace the word optional with expected, there'll be an alternate paper with exactly the same wording, pretty much, once we actually get stood expected itself. So this applies to both in principle. What does it actually give us? Let's have a look at the abstract. So it says I propose adding transform and then and or else member functions to stood optional and stood expected to support this style of monadic programming. So transform and then and or else. And if you do have a functional programming background, you might be more familiar with map and bind for transform and then. They're the same meaning. What about the or else? In the context of error handling, you might want to call that catch, because it's where you put everything else at the end. So it plays that same role. All right, how do you actually use this in practice? Go back to our example from earlier. This is where we got to with the slightly cleaned up version with early returns. So this is like the best we could do without this, in a way. What would that look like with the proposal that we just looked at? That. When you look at that side by side, that's a big difference, I think. I think you'll agree. So you can see the and then, and then, and transform members. And they're just being passed lambdas that actually then do the work. But now everything's going in the proper sequence. The data flow comes in at the top and goes on to each call. But of course, if the first one fails, it's going to skip over everything until the end. The second one fails, it skips over the rest. So there is a natural flow there. This is much nicer, and this is what we tend to do in functional or functional-inspired languages. Something like this is coming to C++. So at least for optional, hopefully for expected too, we get that. It's a lot nicer, but it's still got quite a lot of error handling boilerplate. Partly because the lambda syntax in C++ isn't as nice as in some other languages. So yeah, we're getting there. But bear in mind, this is really the bleeding edge. This is an unwritten proposal on top of another proposal that hasn't been accepted yet. we're a little bit off in the weeds, and we're still not quite there yet. So the other thing to consider is the competition. Today, we have classic exceptions. We could write the same example with classic exceptions like this. This is really where we want to be. Something much more like this. Again, just to compare those two things. The best we may have to offer compared to what we have today. That's the real problem in a nutshell. So how does P0709 address this? This is what the same example looks like with that. Again, just in case you missed it. In fact, that little try keyword there, that's optional. It doesn't even need to be there. And in fact, the current feeling seems to be against it. We'll come back to that, I think. You can look at the top, you can't really read, but there's very little difference. We're just throwing something slightly different. In fact, let's dig into that a little bit more. So, zooming in on that, the function itself, let's highlight the differences. We now have this froze decorator on the declaration. Instead of returning stood expected of int and some error type, would say froze. Seems familiar if you come from other languages. This is not quite the same as the deprecated throw keyword that we could have put there. Some similarities. This basically just means it's as if you had written return of stood expected of int and some error type. And we'll come to that a little bit more in a moment. And then we've got the throw keyword in there, playing the same role as the throw keyword we have now, but the thing it's actually throwing is a value type, statically known. This is where the static part of static exceptions comes from. Because with exceptions that we have today, they have to be allocated as a dynamic polymorphic object. This is just a value type. And the way it's returned, again, it's actually returned down the stack as if you had returned something like a stood expected. Again, we'll put that up in a little bit more detail in a moment. And then down here, the try keyword, which I said was optional, but really that's playing the role of those monadic operations we looked at a moment ago. Really rewriting to something like that. It's doing a lot of work for us, if we have it at all. If you just put a little bit more code around the bit at the bottom, so if we call that in a function, and we don't actually catch it, we need to put throws on that function as well. This can be enforced at compile time. So again, unlike the deprecated throw keyword, it was all runtime checked. This can be checked, again, statically at compile time. So you can't get this wrong. So, yeah, just to highlight those there. And just to add a little bit more, you can, of course, put that in a try-catch block. Same as we can do today, but note the error type there, stoodera. We're going to dig into that a bit more in the second half of this talk. But again, that's a value type. So you only catch one value type in this. So that is P0709 in a nutshell. I went into it a bit more in my previous talk. Herb's been talking about it a bit more in his talks lately. What I want to drill into a bit more now is how this all fits together and what actually makes it work and what gives it some of the performance characteristics that people have been talking about. Before we do that, I just want to drill one thing home. There is this sort of SOAmorphism here between these new keywords, like throws, and the new version of throw, and this optional try keyword, and what we looked at before with this stood expected, make unexpected, the monadic operations. You can think of it, it's not necessarily exactly the same, but you can think of it as if the compiler is just rewriting those keywords on the left-hand side. We'll come back to the code that we see on the right. So the big problem that we had before with stood expected was the verbosity of it, even with the cleaned up versions. Get the compiler to do that work, we can get all the benefits of that. Determinism, better performance, predictability, and so on. But with the succinct and sort of nicely factored syntax of exceptions, that's the key to all of this. And in practice, because the compiler is doing that work for us, it actually has more freedom to go beyond that with further optimizations. So it can actually do an even better job than we could by hand, potentially. Some people have said it's a less than zero overhead abstraction, negative abstraction. We'll actually have to wait and see until we get implementations to test that out, but that's the theory. Okay, so going back to this example. So we said that we're going to come back to look at this stoodera type, because a lot of the magic happens because of this. I said it's a value type, that's important, but it has other properties. To really understand that, we need to look at another proposal. This is P1028. It's got quite a long name, SG14 status code and standard error object for P07090 overhead deterministic exceptions. So it sounds like this is purely a supporting paper for P0709. It's actually not the case. Don't let that fool you. And really, I think that name should probably be changed because this really stands on its own. If we don't get P0709, there is still a lot of value to be had in getting this. So what is it? All right, so we looked at that. From the abstract, it starts off by saying, a proposal for the replacement in new code of the system header system error with a substantially refactored and lighter weight design, which meets modern C++ design and implementation. So this is not something entirely new. This is a replacement, a refinement over something we already have, which is in the system error header. Now, who here is familiar with system error? A couple of people. That's pretty common. I've actually had cases where nobody's put their hands up for this. We've had this since C++11, and it's used in parts of the standard library. This is actually a really useful set of types already today. This is just making it better. It's a shame so few people have actually heard of it. So I'm going to give a little bit of a primer on that as part of this. So before we get to that, so we're talking about stoodera. Let's just have a quick look at what exactly stoodera is. Stoodera is actually a using alias for errored status code, erased system code value type. Right, so we cleared that up. We know what it is now. Don't worry, we'll unpack that a little bit. But let's go back to 2011, C++11, and look at, right, this is where it gets a little bit subtle. Some of the names here are subtly different. The new one that we're going to talk about is stoodera. The one that we've had since C++11 is stoodera code. Okay? Stoodera code is, well, here's like a sketch of what stoodera code is. It's got loads of methods as well, but the essential state of stoodera code is just an integer and a pointer to something called an error category. So you can see, hopefully just by looking at that, that this is a type that can fit into 2 registers, most architectures. That's important. So it's not just a value type, but it's a value type that is sort of easy and cheap to copy around. But what's the error category? We'll come back to that. Won't look at all of the methods, but some of the interesting ones. There's a couple of accessors. You can obviously get the value out. You can also get the error category out as a reference, but really it's still just an accessor. But then it has a message and also a Boolean operator. Where does the message come from if we're not holding any strings in there? We'll look at that. Boolean operator is an interesting one because if you think of it, this is a type specifically for error handling and it has a Boolean operator on it. You would think that if it held an error, it would evaluate to false and otherwise it would evaluate to true. Fortunately, that's not the case. What it actually does is tell you whether that integer value is 0 or not, which in some cases may imply whether it's an error or not, but it depends. And it all depends on this error category. The error category is like a domain for errors. So let's drill into that a little bit more. Here's some examples of some error categories. So the first one on the left-hand side is actually in the standard. As a C++11, there's an enum called RC, which actually contains all the POSIX error codes. We've got all of the POSIX error codes in the standard. Most people don't even know it. So we've got that as an enum, but you might want to have your own error domain with a different enum with different types of errors, like the one on the right. Some errors made up, but every program should have this, I think. So these are error categories. And if you have one of these, you need to have an object or a class associated with it that basically distinguishes what's in there. So what you do is you derive something from error category, and then you implement some virtuals. Again, there's quite a few, but the important ones are equivalent and message. So now you can see where the message comes from. Remember, on error code itself, you can ask it for a message. That just forwards on to the error categories message, and it passes in the error value. And now, because the error category knows about the enum behind it, then it knows, I can convert that value into some sort of string. It's still going to be independent of other contexts, but it could just be a big lookup table or a map or a switch statement. However you want to implement that, you can do that in the error category. That part's straightforward. What about these equivalent methods, though? What do they do? You can see there's a couple there, and there's also this type error condition. We haven't talked about that yet. So because errors can belong to different domains or categories, there's often correspondences between an error in one category and an error in another category. Let's say you have a bad address down there on the POSIX category. You may have something that corresponds to that in yours. Well, you can define an equivalence between those, so you can actually directly compare two errors from different categories and say, yes, they are equivalent. They're not exactly the same, but they are equivalent. That could be really useful if you just want to say, does it match this type of error? So that can be, one-to-one relationship, one-to-many, many-to-many. However you need to define that, you get to choose how you map your equivalences. But sometimes you do actually want the direct, bit-by-bit comparison. Is it the same category and the same value? So we need to be able to compare both ways. And that's why we have this other type, error condition. Error condition is exactly the same as error code, except it's a different type for the purposes of overloading. So we can have an equivalent method with error condition and an equivalent method with error code. Which all works. It means you can use the equals operator in both cases, but it is a bit subtle. Bear in mind, most people haven't even heard of this in the first place. And then you expect them to get this sort of subtlety, and experts often trip up over this. It's a bit subtle just having a type just there only for the purposes of overloading. And it turns out that most of the time we're only really interested in the actual equivalence anyway, not in the direct equals comparison. So that's a little bit of a problem. Well, we looked at those. So there's actually a number of problems with this design. It's really nice in principle, but there's a few flaws. We looked at some of them. So one of them is that those error categories, so we saw there was a pointer in stoodera, but the way it's defined, they pretty much have to be defined as singletons. And the reason for that is because to compare two categories, you have to compare their pointer values. The identity of the category is its pointer, which works fine most of the time, and is nice and convenient, but you have to implement them as singletons for that to work. And that can have problems if you have, say, a header-only library within a dynamic library. Then each dynamic library will have its own address for that singleton. And people hit this all the time. You'd be surprised. That's a real problem. So that's the first problem. The second one is, because of that message method, the whole thing depends on std_string. That might not seem like a problem. Std_string is a widely used standard type we've had since C++ 98. What's the problem? The problem is it is actually quite a big dependency, and it pulls in lots of other stuff like locales and things like that. And this is going to be used in cases where very often people are trying to avoid things like exceptions because they want to pay the overhead of that. And you're forcing them to pull in most of that same machinery again. In fact, I think it even pulls in std_except. So that can be an obstacle for some of the target groups for this type. So that's why I listed it as a problem. Already mentioned that the Boolean operator is virtually useless because it doesn't actually do what you think it does some of the time, which is perhaps worse than all of the time. We also alluded to this error condition type, just there for overloading purposes. Yeah, it serves a valuable purpose, but it's a bit subtle and tricky. Because this whole thing was designed in the time of C++11, where const-expr was just in its infancy, none of it is const-expr. Most of it should be. So yeah, these days, if we were designing from scratch, we'd make it all const-expr, or most of it. That code, the error code, is just an integer. So it can only be an integral type, which is fine if you just want to map it to an enum, but you may want something richer there. There we go again. So the last one, oh, here we go. We said that categories are actually domains. It's probably a little bit easier to understand domains. So why don't we just call them error domains? It's a minor thing, but we're looking at all the problems. We'll list that as well. So that's the set of problems that this new proposal aims to address, each one of these. So let's have a look now at the new equivalent. So it's actually called StatusCode. It's a template. So we said that one of the problems was you can only put an integer in there. Now you can put anything, but we should put some limits on it. So it has that value of that type, and it also has StatusCode domain. So yeah, now we call them domains instead of categories. But other than that, it looks very much the same as we had before. So that's a good start. So let's have a look at that type def, or using alias we looked at before. That was in terms of errored status code, and we just have status code. So we're not quite matching up yet. What's the difference? Errored status code is exactly the same as status code, except that it can never be in a non-errored state. If you only ever want to give an error, and this type will guarantee it's only an error. You don't have to test to see if it's an error or not. So that actually makes the whole Boolean operator thing moot. In fact, there isn't a Boolean operator overload on this type. But it's enforced in the constructor that it's not an error. So makes that a lot simpler. But otherwise, it's the same. So then we just have to look at the erased system code stuff. So you may guess that erased is some sort of type erasure template. And it is. And if you're not familiar with type erasure, it's just a way of having a polymorphic type where you erase the actual derived type that can hold the actual payload, and you just deal with something simpler. So what it actually does is its template argument, so in this case, system code value type, it sets aside storage of that size. So this is saying I can hold anything as long as it fits in the same size as a system code value type, which actually turns out to be an int pointer t in our case. So that's what we're saying. So instead of before it had to be an integer, now we're saying it's anything that can fit in an int pointer t, and it can be different types. And what type it actually is depends on the status code domain. With me so far? This is probably the trickiest bit to explain. So effectively, once you boil all that down, this is what we have for stoodera. So it's actually an alias for a template, but we effectively have status code domain pointer and an int pointer t to hold some other type, but in a non-type panning way. So it looks very similar to what we had before, but much more flexible now. Because not only can we hold integers in our storage, or enums, should I say, we can hold pointers as well. Now, if you think of that in terms of error handling, we can hold exception pointers in there, which is really valuable when you want to interoperate our new exceptions type that only passes around values with traditional exceptions. As something passes through a throws function, the exception can be caught, packed into an exception pointer stuffed in one of these, and vice versa as it passes through another one. So there is an interoperability story there. This is what enables it. But let's have a look at how it addresses some of the other problems as well. So domains are now called domains. Okay, that was an easy one. One thing we didn't talk about is that those domain pointers, they're no longer the identity of the domain. Each domain type or error domain type must provide a uint64t, which has been randomly generated using a hashing function at design time. It's guaranteed to be unique, like a UUID. So that's the thing that identifies a domain. So it's no longer a singleton, or what can be a singleton, but that's no longer an issue. The value type can now be any small, trivially copyable, or movable type. We're going to unpack that a little bit more in a moment. So we said in our case it's an int pointer t, or anything that fits in that. So it's small enough to fit in a register still, but we've got these additional properties of being trivially copyable, and that means that if we copy it using memcopy, just memcopying the bits, that's good enough, but also trivially movable, which is a concept we don't currently have in the standard. But that's the same as saying, well, we can memcopy the bits and then leave or overwrite the original. Doesn't have a string dependency, at least as currently written. I say that because as currently written, it defines its own new string type, string ref, which is quite lightweight, but it's quite a big thing to have in a paper on error codes. So that may get factored out, something may change there, but right now it has no dependency on string, which is nice. It's mostly context-aware, as it should be. No Boolean conversion, as we said. Doesn't have to be, because in our case, it's always an error. And there is no separate error condition type, because now comparing these things is always an equivalence operation. It's always going to call that equivalent method. If you do want the bit-by-bit comparison, you can just compare the value and domain manually. Very rare you actually need that, so that's fine. So with just a few tweaks, it actually solves all of those problems. Takes something that was already very useful, just not very well known, and makes it even more useful. But for our purposes in discussing P0709, it enables the ability for that value type to get passed around entirely in registers, because not only is it small enough, but it can be moved just by copying registers. That's the important enabling part of this. So I said this idea of trivially movable is not currently in the standard. So let's have a look at that a bit more. There's another proposal. In fact, there's two. P1029 and P1144. Both covering the same ground in this respect and some other things. Best way to talk about these is put them side by side. So P1029, move relocates, just has an attribute that indicates that move is trivial, i.e. it can just be a memcopy. That's the bit that we need for our purposes here. And that's the only thing that this defines. So for built-in primitives, this is already the case. An integer can be trivially moved today. And the types that we're interested in can all be trivially moved. But we just need an attribute to be able to tell that to the compiler. Whereas P1144 optionally has an equivalent attribute and also has a number of other things. It's got a detection trait. It actually defines the relocatable concept. Got some algorithms. And I left to last the bit in the middle. Can reset moves from using memcopy. What it actually does there is it says, well, once you've moved from this thing, I'm going to memcopy a default constructed version of it into that space. So not just zeroing it out, but actually the default constructed version. That effectively makes this destructive move. Destructive move has a long and ignoble history in C++ standardization. It's been rejected quite a few times in different forms. So knowing that this may have a bumpy ride because of that, P1029 is also still on the table as a backup to say, well, we can still get at least this part. That's the purpose of the two streams. But it would be nice if you get this. Something we've been after for a long time. And maybe this is the right time for it. I haven't been following this week, but I don't believe this was discussed yet. So yeah, Bryce says no. So that's still on the table, but we're not going to discuss it until we've got C++ 20 out the door, I think. So that really is what stoodera is all about. A bit of a deep dive on what looks like quite a small part of this overall proposal, but a really fascinating one. As I say, that proposal really stands on its own and will be useful in its own right, but particularly enables some optimizations in P0709. But there's also a number of other proposals we talked about. So the big one, P0709, P1028 is the StatusCode one. We also looked at move relocates and object relocation in terms of move plus destroy. There's a family of proposals there. But we also looked at stood expected, which is still at the proposal stage, plus the monadic operations currently for stood optional. There will be an additional one for stood expected when that comes along. That's also a part of this story. And there's another one I want to give an honorable mention to. We haven't talked about it yet. I'll explain why I'm going to bring this one in, even though that paper number is dead. So we had contracts in C++ 20. We've taken them out. There is work to get them back in, hopefully for C++ 23. That's ongoing. One way or another, hopefully we're getting contracts at some point, in probably the same sort of time frame as the rest of this. So they are relevant. And the reason they're relevant, and this is talked about in P0709 actually, is many of the places, perhaps most of the places in the standard library today, where we throw exceptions, really they should be contracts. And there's fairly wide agreement, I understand, in the library groups that should be the case. Hasn't been discussed at length yet, but the initial feeling is, yeah, we want to actually change those to be contracts instead of throwing exceptions. That means you take out most of the places that exceptions are thrown from the standard library, and probably most people's code as well. There'll be contracts instead. Then most of what's left is going to be throwing bad alloc, or allowing for bad alloc being thrown. There's another optional part, P0709, that discusses that. You may have heard of it. There's talk about, well, do we actually make that not throw by default, just terminate? Sounds very controversial, and certainly it's been discussed at length, but actually there's a lot more support than most people thought. We took that out of the equation as well. What's left is just a few places where you really need to explicitly communicate your error handling flow. And then that's when P0709 really shines, especially if we do get that try keyword in there, which is currently being pushed back on. But I think it's being pushed back on because people see exceptions used today everywhere. We're saying we're just going to put the try keyword on everything. Take most of those out. The few that you have left are the ones you really want to know about. So I'm hopeful we'll get try back on the table. But they are all the proposals I wanted to talk about today. So on my site, levelofindirection.com, there are all the references, including all the paper numbers, other background material, and so on, under refs, dawn.html. But that's the end. Thank you very much.